Okay, so this is 1549. So this is not a standing wave, but just a transverse wave. This is a sine wave with an amplitude of 2.5 millimeters. 2.50 millimeters, which is, if you divide by 1,000, it's 2.5 times 10 to the minus 3 meters. The wavelength is 1.80 meters. Travels from left to right along the length and horizontal stretch string with a speed of 36.0 meters per second. This is take the origin, x equals 0, left end of this undisturbed string. So you start with this string that's kind of flat, and then you start disturbing it. What are the frequency, angular frequency, and wave number of the wave? So remember, the wave number is 2 pi over lambda. The angular frequency is, well, we get the regular frequency because we have lambda and we have v. So we have that v is equal to lambda f. Therefore, f is equal to v over lambda. And then we have omega is equal to 2 pi f. I think that's all we need for this one, right? Frequency, angular frequency, and wave number. Okay, so k is equal to 2 pi divided by lambda, which is 1.80 meters. 2 times pi divided by 1.8. So that's 3.491. And the units are radians per meter. Then we have the frequency is 36.0 meters per second divided by lambda, which is 1.80 meters. So 36 divided by 1.8 is 20 hertz. And then omega is 2 pi times f, or 2 pi times 20. So 2 times pi times 20 is 125.7. And those units are radians per second. Okay, so that's the first part. Second question. What is the function y of xt that describes the wave? Okay, so y of x and t, so the amplitude was given. It's 2.5 times 10 to the minus 3 meters. And then you have the cosine. Cosine of kt, it's kt or kx, so it's 3.49, no 10 to the minus anything, times x. Oh, this has units. Let's put the units on 3.49. So it's 3.49 radians per meter x minus omega, which is, we'll round it off to 126 radians per second t. Okay. Next, what is y of t for a particle at the left end of the string? So that left end of the string, so this is c, that's x equals 0. So you get y of t is equal to 2.50 times 10 to the minus 3 meters. With x equals 0, you get the cosine of negative 126 radians per second t. And if you remember, for the cosine wave, it's symmetric around here. So because it's symmetric, you can rewrite this as 2.50 times 10 to the minus 3 meters cosine of 126 radians per second t. And that's just because cosine is an even function. So that's C. D, let's see what that asks for. What is y of t for a particle 1.5 meters to the right of the origin? Okay, so then we just stick in 1.35. So you get 2.5 times 10 to the minus 3 meters times the cosine of 3.49 radians per meter times 1.35 meters minus 126 radians per second t, which if we multiply out that first term and the cosine, we get 2.5 times 10 to the minus 6, and then 3.49 times 1.35, 4.71, and minus 126 radians per second t. Now, again, you could change the order so you can have this one first. So we could switch the signs of what we have inside. So you have the cosine of 126 radians per second t minus 4.71. But it turns out that if you take 3 times pi divided by 2, you get 4.71. So this actually here is equal to 3 pi over 2. Now, how did that happen? So what we're doing is we're looking at this number, and is there any reason that we would have known that at all? I don't think so. This is the answer in the book. I'm not sure how they realized that was 3 pi over 2. If you go back to see, we had the wavelength of 1.8, the wave number, or the wavelength was that. It's 1.8 divided by 1.35 something. Some kind of special number. It's 1.33. Okay. So that's why it ends up being that way. I didn't know that until I looked at the answer. But, the previous answer is correct. What is the maximum magnitude of transverse velocity of any particle on the string? So, in this case, we can go back to the calculation of just a transverse wave and not the standing wave, and there was some result for the acceleration of velocity. So I'm just going to go back to page 476, and it says v sub y of x and t is equal to omega a times the sine of kx minus omega t. So you can see the maximum velocity is just omega times a. So we'll just say v sub y max is the amplitude. So we have omega, which I don't remember what it was, so we'll go back and look here. Omega is 125.7 radians per second times the amplitude, which was 2.5 times 10 to the minus 6 meters. So you can see the units work out meters per second. So 125.7 times 2.5 e to the minus 3, and I get 0.314 meters per second. So that's v sub y max. And then the final part of this question is find the transverse displacement and the transverse velocity of a particle 1.35 meters to the right of the origin at time t equals whatever. Okay, so we have t equals 0.0625 seconds. We have x equals 1.35 meters. So we can just plug those into the appropriate equation. So y of 1.35 comma 0.0625 is equal to 2.50 times 10 to the minus 3 times the cosine of 3.49 radians per meter. We just got to be careful units here. So it's 3.49 radians per meter times 1.35 meters minus 126 radians per second times t, which is 0.0625 seconds. So everything works out. This is they have to end up with unitless. And so let's see what we get inside there. 3.49 times 1.35 minus 126 times 0.0625. Yep. So that's 2.50 times 10 to the minus 3 times the cosine of negative 3.1635, and those are radians. So we need to make sure our calculator is in radians. So 2.5 e to the minus 3 times the cosine of negative 3.1635, and I get negative 0.0025 meters, or negative 2.5 millimeters. Okay, so that's correct. And the velocity, so we're getting the velocity at 1.35 comma 0.0625. So the velocity equation was up here somewhere. So it's omega times a and I just calculated this thing, so I don't need to recalculate it. So it's going to be equal to omega, which we said was 126 radians per second, times a, which is 2.5 times 10 to the minus 3 meters, times the sine of negative 3.1635. Now that's close to pi. It's not exactly pi. Maybe it is if you if we didn't round anything off. So you get 126 times 2.5 e to the minus 3, which is 0.315 meters per second. And if we do the sine of negative 3.1635, you get 0.0219. So 0.315 times 0.0219 is 0.0069 meters per second. So I think somewhere in here, if we hadn't rounded off, we would have actually gotten 0 here instead of, because if you think about, the maximum velocity, I think we calculated that earlier in one of the earlier parts, and it was a lot higher than that. So, okay, so that's it for that problem.